Hello, this is Heather Ali, and in this video, I'm going to present component diagram to you today, which is a type of UML diagram. Before we start discussing component diagram, can you think what is a component in a system, or have you worked on a components before? You can pause the video and think about it, or let me give you 10 seconds to do that. A component can be any file, executable, or a library in a system. Each component usually represents key functionality in the system. Multiple components work together to make a system. Why do we need component-based programming or development? These bubbles show exactly why we need components. First reason is reusability. This can be explained by an example of software as a service. Let's take, for instance, machine learning as a service. In that, we can consider a component as every machine learning algorithm. We make algorithm components in such a way that there is reusability across data sets. Second reason is replaceability, which means that we should be able to replace those components later by other implementations. Third reason is encapsulation, which means users should be able to use the functionality of the component without knowing the implementation details. Other reasons are deployability and maintenance, which also emphasize that components should be independent enough of other components so that they can be deployed or maintained separately. Now let's talk about different definitions of component diagram. In general, it is used to represent different components and their relationships visually. It's actually a structured UML diagram which shows the physical aspects of the object-oriented system. By physical aspects, I mean the organization of different components, including their locations in the system and relationships with other components. We can also call component diagram as a type of a class diagram, which visualizes component in the system. But class diagram is generally solely for the object-oriented program. However, component diagram is mainly used to represent large-scale systems where modularization is always necessary. Component diagram varies at different moments of time, since you can keep on adding or removing the components, so it can also be used as static view of the implementation at any given point in the system. Let's think of some applications where we can apply component diagram other than SaaS. SaaS means software as a service. You can pause the video and think about it. Let me give you 10 seconds to do that. Component diagram is popular in the systems that use service-oriented architecture, SOA, such as SaaS, software as a service. However, there could be other applications where we can use component diagram to model database schema, executables of an application, and system source code, other than the main application of modeling components of a system. Executables are constructed using component diagram with forward and reverse engineering. But yeah, main purpose is to visualize, specify, and document the high-level implementation details of different components in a system. Let's discuss how can we make a component diagram in graphical format. It's a collection of arcs and vertices, where vertices show the components and arcs show the relationship between those components. Major elements of component diagram include components, provided interface, required interface, port, connectors, constraints, relationships, and dependencies. This figure is an example of a safety inspection terminal system, shown as component diagram, where on the right-hand side, there is a required interface. Required interface means the input required by the system to perform its operations. For example, in this case, account and inspection ID are required. These data points are entered and pre-processed by a square called port. Similarly, on the left hand side, port is used again, but this time port is used to get the data points out of the system. For example, state and details of the safety inspection in this figure are given by the system after running some components in the system. In this figure, we can see 4 components, which is usually dependent on number of functionalities you have in the system. Staff, safety inspection, defect, and map, all of them can be treated as separate independent components. Components are usually connected by assembly connector, which can be shown by this ball and socket symbol. Combining all these 4 components can also be a component or a subsystem as a part of whole large-scale system, as it can be seen in this figure. To sum up this slide, ports take data in and out of the system, and interfaces provide that functionality to end users. How different components are related are also shown in this figure. Let's discuss a rather more complex example of component diagram. This is an example of an online shopping store like Amazon, where there are 3 subsystems: web stores, warehouses, and accounting. In this case, subsystems are just like departments in a big company. Departments in a company are always independent units and have their own objectives. But they do collaborate with other departments to make a productive system as a whole. Similarly, this happens in this component diagram. Let's discuss web store subsystem. It has 3 main components based on 3 main functionalities: authentication, shopping cart, and search engine. User comes and use the required interface to search something and get products in result. Similarly, he can add orders to shopping cart. Authentication is related to shopping cart since cart needs to be saved if the user is logged in. Accounting subsystem contains components of orders and customers, but these components can relate to the components of other subsystems. For example, orders relate to shopping cart and customers relate to authentication. The arrow between components shows the dependency of one component on another. The arrow between customers and authentication means that customer is required to do authentication, or the arrow between the orders and inventory means that that order will be made if there is availability of the product in the inventory. In addition to these, we can put constraints as well, that how many customers relate to how many orders, such as one-to-one relationship or one-to-many relationship or many-to-many relationship. Let's wind up our video by discussing about potential relationships components can hold among each other, which are also inspired by object-oriented programming. This slide shows these relationships and their symbols. I would not go into the details of these relationships, as they have been already covered in the class. These relationships include aggregation, which is shown by the unfilled diamond symbol, composition, which is shown by the filled diamond symbol, association, which is shown by a line, links, which is shown by arrow, dependency, which is shown by dotted arrow with the circle, and constraint, which is shown by a note. To be concise, a component can be associated, dependent, composed of, linked, or aggregated to another component. These are the reference links from where I took these example component diagrams from. You can use these links to study more about component diagrams as it can be used for multiple other purposes of database schema and system source code. In conclusion, component diagrams are the great way to understand the high-level implementation details of the large-scale and complex system. Thank you, and I am open to questions in the discussion page of Canvas.